Holger Kammeyer, who's going to give us the first talk. Holger's from Düsseldorf, of course, who's going to talk to us about profiniteness of higher rank volume.
Thank you, Martin. And well, thank you to the organizers, even though only half of them are here, for giving me the opportunity to speak here and for giving me the honor to give the first talk, actually. So I want to open up this conference with a question that I grew very fond of. It's been around for a while. So actually the first time I heard about this was, I think, from you, Martin, at the conference in Bonn, like 10 years back or something like that. And it says the following: so let M and N be finite volume hyperbolic 3 manifolds. And suppose that their fundamental groups have isomorphic profinite completions. So usually when I give talks about this, then at this point I would explain what the profinite completion is, but maybe this is the one workshop where I don't have to do this. So still an equivalent way of saying that is both groups should have the same set of finite quotient groups. Yeah, this is the way that's usually rephrased. And then the question is, does the volume of the one manifold, the hyperbolic volume, equal the volume of the other manifold? And yeah, like I said, I've heard this a couple of years back, but I think it was most prominently advertised by Alan Reed actually at his ICM address. So just for reference, let me put his name there. 2018. And okay, of course there is this general theme of taking your favorite group invariant and asking yourself whether it's a profinite invariant, so whether it should agree for any two groups which have the same profinite completion, right? So this would just be one of them. And I do believe that this particular question is, however, even more interesting than the other ones. And let me tell you why. Because it's somehow related to other conjectures that have been around for a while. So some evidence why the answer to this question should be yes maybe comes from what I want to call the L2 torsion growth conjecture. So I'll just sort of say this in words. So it means if you have a spherical manifold, a manifold whose universal covering is contractible, and it should be of odd dimension, then the growth rate, the exponential growth rate of torsion in homology along residual chains in the middle degree of that manifold, that should be given by the L2 torsion. Okay. So whatever that means, if that is true, then the answer, or it's not hard to see that the answer to this question is yes. Okay. Because, well, if this odd dimensional manifold is 3-dimensional, then the middle degree is the first homology. First homology tells you about the abelianization of the group. So since we know that abelianization is a profinite invariant, it's maybe not so surprising that this should be true. And it actually is true. But whenever you give evidence, you should also look at the other side. So let me mention that in contrast. There is a result of Grigory Aframidi, Boris Okun, and Kevin Schrewe from, I think, 2020, saying that there is a third conjecture, what's called the Singer conjecture. And the Singer conjecture tells you again something about spherical manifolds. It tells you that the L2 cohomology of such a spherical manifold should be concentrated in the middle degree, so it can only be non-zero for an even dimensional manifold, and then it can only be non-zero in this middle dimension. And it turns out that if this Singer conjecture is true, then this L2 torsion conjecture cannot be true. So they clash, these two conjectures. Yeah, so I think the way it goes is they show if these two conjectures hold, the single conjecture and the two torsion growth conjecture, and the third conjecture is true, and then they disprove the third conjecture. So they cannot be true both at the same time. But I should say also that this is not really in contrast to what we're asking here, because the counterexample is not in dimension 3. Yeah? So maybe let me tell this. Not in dimension 3. And that's important because, well, the Singer conjecture is known in dimension 3. Algebraic numbers of 3 manifolds have been calculated, or now they're easily calculated by Egel's work. So therefore, this is not a contradiction. But what I was going to say with this is just that this particular question is not only relevant by itself, but it's also connected to other questions like which have been around for a while. Yeah? So this is my bit of motivation for why we should finally answer this question. Yeah? Since I'm just seeing you in the audience, it's also known that there are only finitely many hyperbolic 3 manifolds of a given volume. So answering this question by yes would give the immediate conclusion that there are only finitely many hyperbolic 3 manifolds with the same profinite completion, but that has been shown meanwhile by different methods. Yeah? As far as I know, you do not know if they have the same volume, do you? No, okay. So this is definitely interesting, and whenever a question is interesting, then so should be all of its generalizations. Okay? So let me ask a more general question. So say gamma and lambda, or gamma and delta. I never know if I want to call my second letters delta or lambda. Gamma and delta in G, the irreducible lattices. In a semisimple Lie group, and let's say we fix a Haar measure on this Lie group. It's unique up to scaling anyway, so let's fix such a scaling. So with a fixed Haar measure, and again, suppose that these two lattices have isomorphic profinite completions. And then we ask, does the Haar measure of the quotient, so G mod gamma, equal the Haar measure of the other quotient, G mod delta? Okay, so sort of the induced G invariant Haar measure of this quotient set. And it turns out that the previous question is just a particular case where G is PSL2C, right? Because PSL2C is even a simple Lie group, which turns out to be the isometry group of hyperbolic 3 space, right? So in that case, we basically get back the previous question. And I think one can make a case why this question is also interesting in higher rank, or maybe in some sense even a bit more, because for most simple Lie groups of higher rank, so semi-simple but even simple, it's known that there exist such examples, gamma and delta, of lattices in the same Lie group, which are profinitely isomorphic, but not only not isomorphic, but not even commensurable. Okay? Gamma and delta non-commensurable. Yeah, so if you look at the original question, I mean, then one can make the case that what one should really ask is if hyperbolic 3 manifold groups are really distinguished from one another by the profinite completion, which would turn this question into an empty question, of course. But in this case, there are really different lattices, so asking for whether their volume agrees makes makes sense and is interesting. And moreover, if they were commensurable anyway, then this would only be the question of whether sort of the common finite index subgroup they have, if they sort of the index is the same, right? So this would not be really a question about volume. So in this case, I think it's more clear-cut, a question about like volume. Okay, so this has been, I mean, there have been various methods known how to construct such examples, but at some point, Steffen Kionke and I decided to do like a systematic investigation, and it really turns out that we can specify what most means here. So most means if the congruent subgroup property is true for these higher rank lattices, then these examples exist in all simple Lie groups of higher rank, except the complex forms of type E8, F4, and G2. Yeah? But in most cases, these do exist. And in those exceptional cases, they really don't exist. So these lattices are what we call profinitely solitary. Okay. Okay, so I hope I've convinced you that this is an interesting question. So let me report on some partial answers. So, as so often in the world of semi-simple Lie groups, the question is totally different in the cases where this Lie group has rank 1 and where it has higher rank. Yeah? So I should also split up my answers into the higher rank case and the rank 1 case. So here's the higher rank theorem. Call it theorem A. So this is joint work with Steffen Kionke and Ralf Köhl. And the theorem says that let G be a semi-simple Lie group connected and again fix a Haar measure on this. Call it mu. And of course, suppose that we have two lattices in there. Call them gamma and delta. Sorry, I have to assume irreducible lattices again. And assume what we want to call, well, the congruent subgroup property, and put a little asterisk here, and I'll explain in a moment what I mean by this. So maybe already for the experts, so CSP means, well, the congruence kernel is finite, and what the star means is we not only want this to be finite, but we also want the proof to work that usually is done to show that such a congruence kernel is finite. So we want to know that what's called the metaplectic kernel has the same order as the congruence kernel. But I'm going to come back to this in a moment. And such that the profinite completions are, of course, again isomorphic. And I might have forgotten, like it's in a simple Lie group with fix Haar measure mu. Yeah. And no compact factors. And yeah, no compact factors and finite center. Okay, so the typical assumptions you will need to get arithmeticity going. Okay. Okay. Then the conclusion is indeed that the Haar measures agree. Okay. So the question is, of course, now, since there is still one assumption which is not so clear-cut, the CSP stars thing, like how many higher ranked lattices are known to have this property. And I think it's fair to say that, well, sort of most of them do. There are some notorious exceptions. But still, it might be worthwhile to point out one unconditional theorem here. So the most famous known case where CSP holds true is for so-called isotropic algebraic groups, which in this geometric setting translates to the assumption that these lattices are non-uniform. Okay? And if we assume that, then this theorem becomes unconditional. Okay, so this is sort of exploiting what's known in CSP to get an unconditional statement there. Okay, and the second remark then is about rank 1. So, second result. To explain this, okay, so in the rank 1 case, there are not so many rank 1 simple Lie groups. There's basically SOn, SUn, SPn, and then there's one exceptional Lie group of rank 1 still, called F4 minus 20. And it turns out that about this very last one we can assert something. And to say what that means, let me recall that corresponding to this classification of rank 1 and simple Lie groups, there's also a corresponding rank 1 exceptional symmetric space, which is usually denoted OH2. Yeah, sometimes it's called the Cayley plane, so the O refers to those octonions, like this non-associative division algebra over R. And this is an irreducible symmetric space whose isometry group well happens to be exactly this exceptional Lie group of type F4, which is called F4 minus 20. And correspondingly, we want to say that M is an octonionic hyperbolic manifold, so an octonionic So since these octonions are 8-dimensional, the octonionic plane should be 16-dimensional, so we should be talking about a 16-dimensional manifold here. So an octonionic hyperbolic manifold is a 16-dimensional Riemannian manifold. M, whose universal covering then is isometric to that very irreducible symmetric space. So with M twiddle being isometric to OH2. Okay. And since the fundamental group of a manifold acts on the universal covering by deck transformations, in this case it acts by isometries, so this gives us an embedding of that octonionic hyperbolic manifold, of the fundamental group of that octonionic hyperbolic manifold, into this isometry group, which we set as F4 minus 20. Okay. And yeah, so since I just come from teaching a topology course, and I was very pedantic and adamant that my students would learn that the universal covering is a base point dependent construction, right? So you can only talk about the deck transformation group, deck transformation action of the fundamental group on the universal covering after choice of such a base point, which would then result in the fact that this embedding is only unique up to conjugation, right? But if in a moment I want to ask about volume, that doesn't matter because conjugate lattices will have the same volume. So this embedding is unique up to conjugation. And for those manifolds, we want to assert a positive result on this more general question on the left board. So theorem, again, by the three of us. Yeah, I cannot abbreviate our three last names. So let's do it like this. Okay, so let M and N be two such manifolds. Let M and N be finite volume octonionic hyperbolic manifolds. And let's call their fundamental groups gamma and delta. And now we need to assume something about these lattices. So manifold being finite volume translates to these fundamental groups being lattices in the isometry group of the symmetric space. So assume that these lattices, gamma and delta, we want them to be arithmetic congruence lattices in F4 minus 20. Congruence lattices. So I'll comment on this assumption in a moment. In this group, F4 minus 20. And of course assume that the profinite completions are isomorphic. Then indeed the octonionic hyperbolic volume of those two 16-dimensional manifolds agrees. Okay, so two remarks on this assumption, arithmetic congruence lattices. So first remark is that being arithmetic comes with no loss of generality, because even though F4 minus 20 is a rank 1 Lie group, it's known to behave in some ways like a higher rank Lie group. In particular, lattices in this Lie group satisfy superrigidity, and they also satisfy arithmeticity. They also have property T. So this assumption that it's an arithmetic lattice is no loss of generality. So arithmetic comes without loss of generality. So these are, of course, deep theorems by Colette and Gromov-Schön. And whether the second property of being a congruence lattice is an assumption or not, that's kind of up for debate, because it's not known whether this group F4 minus 20 also behaves like a higher rank group with respect to this last property of having the congruent subgroup property. So if F4 minus 20 has CSP, then neither is a restricting assumption. Can be deleted. So I don't know. So about this congruent subgroup property, the classical conjecture by Serre just says it's a higher rank 1 thing. So higher rank lattices should enjoy it. Rank 1 lattices should not enjoy it. But now, as this group has all these other properties, one might take this as indication that it also has CSP. I think at least I read a remark from Alex about this. Cite this. On the other hand, yeah, I don't know. Other people, I talked to Pierre-Emmanuel Capras, who says no, not having CSP is very much compatible with all the other higher rank phenomena. So I don't know. Why would we argue? It's open. Okay. Okay. So yeah. So for a higher rank case of this more general question, I think this theorem is pretty much exhaustive. I mean, in the sense that the remaining cases are not our fault. That's the fault of people working in CSP. Yeah, I mean, we need to solve the last open cases of CSP in higher rank. Then in that case, we do get the full statement. And unfortunately, in rank 1, this question really probably turns out to be quite different. I mean, the reason why this is true, as I will explain now, is of course an arithmetic one. And in this higher rank case, there are not only arithmetic lattices, so sort of we need also a different mechanism to show that this would be true. But nevertheless, at least we have this one strange symmetric space where we can insert something, yeah, for a very particular reason. And if you want to ask about the original question, then let me tell you right away, our methods give absolutely no progress on that one. Yeah, so everything really breaks down for that. Okay. So, right. I'm never sure of how much proof is appreciated at these conferences, but since this is a very specialized conference with many experts on working on these things about profinite rigidity, I thought I do want to give some insights into why this is true. Yeah? So let me sketch some part of the proof. Unless there are any more questions on the statements. Yeah?
Why 4 minus 20? Why does it not work for like SPN?
Yeah, so I was going to comment on this. The particular reason why it works for this one is that groups of type F4 have no center. Or in other words, the simply connected groups of type F4 are also the adjoint forms. And so sort of two things. I mean, I'm gonna, in a moment, I'm gonna sketch like a pretty, I would say, easy proof of the most basic case of this theorem. And then the nuisances, which sort of make this hard to conclude the result in general, is if the group has a center and if this congruence kernel is not finite, it's not trivial, but only finite. Yeah, so if we don't have the triviality there. And for this rank 1 thing, we cannot discuss away this center thing. So I guess we could prove for SPn, something like if I have two arithmetic congruence lattices in SPn, with isomorphic profinite completions, then either their volume is equal or differs by a factor of 2, because the center is neutral. But is that a theorem? I don't think so. Any other questions? Yeah?
Can you comment on the reducibility assumption?
Yes. Yes. Okay, so a semi-simple Lie group is an almost direct product of simple Lie groups. Yeah? And you do not want those lattices which just arise as products of lattices in each factor. Okay? So reducible means whenever you leave out one of those factors, then sort of the lattice projects into something dense. Yeah? And why do we need this assumption? Because, like I already alluded, we want to get into this arithmetic setting. And this Margulis arithmeticity theorem needs this assumption of an irreducible lattice. This is necessary to see that such a lattice is given by the ring of integer points of some algebraic group. Yeah? So I'll come to this in a moment.
If you assume, say, arithmetic compensable property and you draw irreducible?
I mean, if you formulate this for arithmetic groups right away, then irreducible is included. So if you have an arithmetic subgroup of a simple algebraic group, then it defines a lattice in the product of the real and complex Lie groups of all the finite places of your number field. So this is then automatic. And if you want to conclude this for a lattice, then of course you need to assume this necessary condition. This miracle work of Margulis says that this necessary condition is somehow also sufficient. Other questions? Okay, so then let me comment on the proofs. Okay, so like I said, various big ingredients go in, sort of the hassle or the big part of the work's been done, and you put the puzzle together, it seems to work. So the first big ingredient is arithmeticity, which says under these assumptions, so I'm talking about, this was supposed to be an A there, theorem A. Under these assumptions, higher rank, irreducible lattice, low compact factors, finite center, we have this Margulis arithmeticity theorem, which states there exists, and uniquely so, a number field K, so meaning a finite degree extension of the rational numbers, and a, let me just write, simply connected, absolutely almost simple, or absolutely simple linear algebraic group G over K, so linear algebraic K group G, such that sort of the Lie group I'm talking about, this G, is built out of this algebraic group by taking the product over all the completions of K at the finite places, meaning at all the embeddings of K into the real and complex numbers. Okay? So, and an isomorphism of topological groups call it phi, from the product of, let me write in this number theory terminology, V divides infinity, meaning the product over all embeddings of this number field into the real and the complex numbers. Then I complete the number field at these embeddings. I mean, I use sort of the field I have at that embedding. And from this product, I get an isomorphism to my original Lie group G. And not only that, but in such a way that my original lattice is sort of given by the integral points of this algebraic group. So, such that if I take my ring of integers in K, so standard notation is this OK. So if K is just the rational numbers, then OK would be the integers really. Yeah. If K is, I don't know, Q adjoint square root of 2, then this would be Z adjoint square root of 2. And if I consider the image of this under my isomorphism phi, then I get something commensurable with gamma. So meaning this image has a finite index subgroup, which is isomorphic to some finite index subgroup of gamma. Okay. So of course, given a simplified talk here, so a couple of lies in this statement. So what you would really get is not quite an isomorphism of topological groups. You would get a homomorphism of topological groups with finite co-kernel and with compact kernel here. Yeah, you can make the compact kernel go away by excluding places in this product where the group becomes anisotropic, becomes a compact Lie group. So I should really say GKV, or let's say GKV isotropic. So then my compact kernel is only a finite kernel, and then I sort of only have to adjust the groups in their, what's it called, isogeny class to make this, to turn this into an isomorphism. But this is sort of, yeah. So let me sweep this under the carpet. Yeah, this is sort of the details in the proof that you have to take care of these issues. Yeah, but morally it's true that you can just represent your Lie group as the real and complex, as the product of real and complex points of a algebraic group over some number field. And the lattice is then just given by the OK points here. So this is another problematic thing. Yeah, G is an algebraic group. So as a functor, it's defined on K algebras. OK is not a K algebra. So I should choose an OK scheme model for this, or I should just embed it into GLN and then use this to define what the OK points are. Yeah. But since the statement is only saying something is commensurable with it, whatever you do here will only change, will not change the commensurability class. So this is kind of a well-defined statement. Yeah? Please allow me to write these things. Yeah? Okay, so this is of course kind of better to work with because this really shows you like how this lattice arises, yeah, and like an algebraic group over a number field is sort of something more concrete and more hands-on you can work with than just some abstract lattice in a Lie. So then, what I've shamelessly talked about all the time, without saying what it means, is the congruent subgroup property. So let me now tell you what I mean by this. So I have now my linear algebraic group G. So just think of it as a subgroup of GLN defined by polynomial equations, polynomials with coefficients in K. I have this thing, so I can form my K rational points, GK, so all solutions of this polynomials in K if you want. And I can assign a topology to this group. And how do I do this? I declare a unit neighborhood basis. And what's my unit neighborhood basis? It consists of all the finite index subgroup of this guy here. Okay, so GOK embeds into GK. So the finite index subgroup subgroups of this thing embeds into this. And I just say that these subgroups should form a unit neighborhood basis of 1. This uniquely determines the topology on this group, turns it into a topological group. And now there's a nice feature about topological groups. They come with a unique uniform structure, so that it makes sense to complete these topological groups with respect to this uniform structure. And if I form this completion, yeah, I want to call it GK hat. Yeah? So really think of it as adding Cauchy sequences, and what a Cauchy sequence is makes sense now in such a topological group. Okay. So that's one thing I can do. There's a second thing I can do. I take the same group, I assign a different topology to this. I say that a unit neighborhood basis is does not consist of all the finite index subgroups of GOK, but only of those which are called principal congruent subgroups. So what is that? If I take any non-zero ideal in this ring here, I can mod out this ideal, and I get a projection homomorphism from GOK to this then finite ring GOK mod A. Yeah, the kernel will be a finite index, even normal subgroup of GOK, and all those finite index subgroups I obtain in this fashion should form a unit neighborhood basis of this group here. This, again, defines a topology. It's weaker in the sense it has fewer open sets, fewer closed sets, so the completion should also be, with respect to the corresponding uniform structure, should also be smaller, in the sense that I get a unique surjective homomorphism from here to here. The one that extends the identity on GK. And this surjective homomorphism has a kernel, of course. And this kernel is what we want to call the congruence kernel. Okay. Yeah, so from the construction that I've told you, the congruence kernel should be a measure of how much it is true that every finite index subgroup of GOK is a congruent subgroup. Right? Not quite true. I mean, if it's true that every finite index subgroup contains a principal congruent subgroup, this is what I should say. So if that is the case, then this thing is trivial. But in general, I mean, these are totally disconnected groups here. So this can be something complicated. So in general, actually, this is going to be a profinite group. A profinite group is either finite or uncountable. So sort of the correct sharp cut is whether it's finite or uncountable, right? So we want to say G has CSP if this kernel is finite. Okay, so if C and G is finite, then we say G has CSP. And for the purpose of this talk, again, let me assume for simplicity now that it's actually trivial on the nose. Actually, in many cases, it will be. So this is not, even though if it's not trivial, this is, again, what causes lots of the technical apparatus in the paper. There are many cases where this is even true. Okay. Any questions about arithmeticity or the congruent subgroup property?
Finite index subgroup to make sure it's always true.
Yes, exactly. So one can always, yes, exactly. So one can always get rid of these nuisances of, I don't know, having a finite center or having a finite congruence kernel by passing to finite index subgroups. But you got to remember that we're asking about volume, and there passing to finite index subgroup changes the volume, right? So you have to keep track of this. And in a moment, we'll see, I mean, gamma and delta define two different, I mean, a priori, different algebraic groups over different number fields. So how can you ensure that you can pass to finite index subgroups of the same index? You know? You want to assert in the end that it has the same volume. So this is sort of where... Excuse me? They have the same profinite completion, yes. Yes, but the congruence kernels of the two groups can be different. A priori. So... Okay, so, yeah, like, you're absolutely right. One passes to finite index subgroups in the general case, but for this talk, let me do it like this. Other questions? Okay. Then, third ingredient, let's something we called adelic superrigidity. That sounds more noble than it is. So Margulis superrigidity tells you sort of that you can extend homomorphisms from lattices to the surrounding D groups, and this holds for homomorphisms into algebraic groups over any local fields. Can be p-adic fields, can be the reals, can be complex numbers. And sort of if you gather them all together, you can also do this for the Adel ring of a number field. So this is, I mean, we wrote this up, but of course this is just observing what follows from Margulis superrigidity. And it says the following. So let gamma and delta define by arithmeticity, still in the setting, their surrounding algebraic groups. So for gamma, we said the number field is called K, the group is called G. And let's call the other lattice, the surrounding group H over a number field L. And then if we have such an isomorphism from one profinite completion to the other, then by Margulis superrigidity, one gets a collection of homomorphisms to various local fields, algebraic groups over various local fields, but we can gather them all together by, well, taking this field isomorphisms and collect them to a ring isomorphism of the corresponding finite Adel rings. And over this isomorphism of the finite Adel rings, we find an isomorphism of the corresponding algebraic groups. So we do base extension over the number field K with this K algebra, if you want, AFK, and we get an isomorphism to the same thing for the other groups. So we do base extension with AF L.
This you are proving using Margulis alone or with the congruence property?
This is Margulis alone. This is a consequence of superrigidity, and that's important for the rank 1 case here. Exactly. That's a trick we learned from your student Manny Aka, by the way. Yes. Exactly. And like in superrigidity, it's not only that, but it's the additional statement that this isomorphism somehow extends what you're given here. So, such that if we take the previous isomorphism of the profinite completions here, then, okay, so here's something which maybe I should have explained. So we can sort of pretend that our lattice is GOK. So it sits inside this group here. Yeah. So if I take the closure of this GOK, of this lattice inside here, I get precisely the profinite completion. Yeah. I can also take the closure in this group, and what I get is what's called the congruence completion. Yeah. If this thing is trivial, then the two things are the same. But the nice thing is that if you complete here, you have a good understanding of how this completion looks like, yeah? Because it will just turn out that it's well, the product over all GOVs, over all valuation rings for finite places here, which is an open subgroup of the Adel points of the group GKAFK. And therefore, we have an embedding under this assumption that the congruence kernel is trivial to the Adel points of the group. And the same here, give it names, QG and QH. And here we've got AFL here, and this is the asserted isomorphism. And this eta sort of extends this psi. And again, minor lie. I should say this only commutes up to a central character. So this is the same that happens in these superrigidity statements. You want to extend a homomorphism to a homomorphism of the surrounding groups. And you get this extension, but not quite. You must allow that you still multiply by some central elements. There's sort of some defect there. And this defect actually, at least, it's not completely erratic. It's a homomorphism from the lattice into the center, by which you have to correct this. Yes, Alex?
Can I bother you on a technical problem that this might be important? Do you have isomorphism also between the so-called arithmetic completion?
Oh, I should have written isomorphism here, of course, by the way. Yeah?
No, you have isomorphism between profinite completion. Can you you deduce isomorphism between the adelic completion and I guess from there for the co-volume? But my question is, do you deduce it from an isomorphism between the arithmetic completion?
When you say arithmetic completion, you mean congruence completion?
I mean the completion of GK, the profinite, which is not really the profinite completion.
Yes, exactly. It's not the profinite completion. Yeah.
But do you get, assuming gamma hat and delta hat are isomorphic, do you deduce the GK hat and HL hat are isomorphic, or only that the adelic are isomorphic?
No, we only deduce that they're adelically isomorphic. I mean, this is what we assert here, right? I mean, what we get is we get a family of isomorphisms between the local completions of these fields K and L here. This is what we really get. So we get sort of a bijection from the finite places of K to the finite places of L, and corresponding isomorphisms from KV to LV prime, and so on. And over these local fields, the G and H are isomorphic.
I thought that the arithmetic completion, what circles, are almost isomorphic in the following sense, because the adelic quotient are isomorphic, but it looks like the congruence kernels in both cases are also isomorphic because gamma hat and delta hat are isomorphic, and modulo the congruence kernel you are proving that they're isomorphic.
Yeah.
Then probably it means that the kernels are also isomorphic. I mean, do you say that or not?
I believe we had an example where the congruence kernels can differ, but I would have to look it up. So,
really differ.
one trivial and one order 2, I think.
No, that's,
Yes.
I mean, I want to use your technique when the congruence really fails. Both, let's say,
okay, you want to use it for this one.
or for, no, even more important for the other case.
Yeah, okay. Yeah, no.
Okay.
No, I mean, this method doesn't give it to you. I mean, this is assuming, this uses super rigidity, which fails for SON(1) and SUN.
But all you said so far also work for the F4 minus 20?
If we are assuming that the lattice is a congruence subgroup right away, yes.
Congruent, but you don't assume the congruence are a property.
No, exactly.
Okay.
Exactly. Yeah, so if the congruent subgroup property is not true in this second theorem, well, then this is just an assertion about a subset of all the lattices here. Right? Okay, so we have this. At what time do I have to stop, by the way?
That big clock.
Plenty of time. Excellent. Okay. Okay, so these are the 3 ingredients. So we have managed to find a very explicit description of the lattice as such an OK points of a linear algebraic group over a number field. We assume the congruence subgroup property is true, which gives us a good understanding of what the profinite completion is. Namely, it's an open compact subgroup of this Adele points here. And we also know that as a consequence of superrigidity, the profinite completions being isomorphic means that those groups, those ambient algebraic groups, are isomorphic over these Adele rings. Does everybody know what the Adele ring is, actually, or should I comment about this? No? Okay, so maybe very briefly, so when I write AKF, what do I mean? I mean I take the product over all finite. So this is again this symbol in number theory. So you do not consider the embeddings of the field into the reals and the complex, but into finite extensions of QP. So corresponding to p-adic norms here. You take the product of all the completions as those v-adic norms of KV, but not quite the full product. Take the restricted products, require that almost all coordinates should lie in what's called the valuation ring in KV. Yeah, so such a local field has this sort of ring of integers, the valuation ring OV, and then almost all the coordinates should lie inside this subring. Okay, this is what it is. Okay. But by projecting to the various local fields, this means in particular that you get isomorphisms of G and H over these isomorphisms of KV and LV prime somehow. Yeah? So this is it. Okay, so what does all this help for the question of volume? Well, what we do now is we know that our Lie group G is basically this product here. So we choose a fundamental domain of the action of gamma on this Lie group here, but we look at it on this side that we expect that we understand better, right? And then we want to calculate the harm measure of this fundamental domain. So let F be a fundamental domain for this action of gamma on this product. It's infinity GKV. And then it turns out if I take the product of this fundamental domain with the image of this map QG there. Yeah, so with this open compact subgroup of the Adele points there. And this is actually also a fundamental domain, but for something different. Namely for the action of the k rational points of the group on the full Adele points of the group. Okay? So there's no letter F here. So this means we take the full Adele ring, meaning we do not take the product over all, where is it there? Over all finite places, but actually over all places, real complex and p-adic places. And sort of this is the nice thing about this new ring, this ring of Adele that you can associate with a number field. This group of k rational points, which is sort of usually big, yeah, so it's going to be dense in this group here, becomes discrete in this group here, if I take the diagonal embedding of gk into gak, yeah? So this is really a discrete subgroup, in that sense, a lattice of this locally compact group. And therefore it makes sense to choose, or to try and find a fundamental group for this. And it turns out that the choice of an arithmetic subgroup singles out or gives you such a fundamental domain, yeah? And then you take the fundamental domain at the real, at the real and complex places for this arithmetic group, and then you take as the rest, yeah, you take sort of the congruence, the open compact subgroup of the Adele points that defines this lattice as a congruent subgroup, yeah, all assuming that this lattice is a congruence lattice, as we do here by requiring that the congruence kernel is trivial. Okay, so if you don't believe this, it is a proposition, but maybe as a reality check, I don't know, if you scale the idea that defines your congruent subgroup by an integer, say n, then this fundamental domain is also going to be scaled in measure by this integer n. Yeah, but at the same time, this integer n is uniquely a product of prime powers, right? And at this part of the fundamental domain will correspondingly make the measure smaller again. Yeah, so if it has, I don't know, p to the k divides this n, then this is going to give you the factor p to the minus k here, which is sort of going to cancel out what you changed there. Yeah, so maybe it's believable that in such a manner you do find a fundamental domain of the k rational points of G on the Adele points. Okay. And then, of course, the nice question is, well, what is the measure of such a fundamental domain? So sort of what is the co-volume of GK in GAK? And to answer this one, first of all, needs to fix a unique choice of measure on these Adele points, and that's actually possible. And let me explain to you how this works. So one takes a non-zero K form. So this is in the d exterior power of, well, take the tangent space of your Lie algebra and its dual. So tangent space at 1 is also known as the Lie algebra of this G. Take this dual, and D is of course the dimension of the group G. And then, well, you've got one top dimensional form at this one tangent space. You can use your group multiplication to get such a form at every tangent space. So you do get what's called an algebraic differential form on G. So any such thing extends to a differential form. Omega on G, where D denotes the dimension of G. Okay. If you have, well, such a differential form defined over K, then you can always complete your number field at the various places that you get corresponding differential forms on the corresponding KV points of your group, right? So let me put it like omega V induces, and let me get rid of this again. So omega V induces well, a differential form on the GKV points, and therefore integration with respect to this differential form defines you a Haar measure on these GKV points. Yeah, so this induces a Haar measure, which now depends on this differential form and the place at hand. So mu omega V on GKV. Okay, so you've got a measure for each place of the number field. So what you can do is you can take the product of all those measures. And what you get is what's called the Tamagawa measure. Tamagawa measure. Call it mu tau as the product over all V of these mu omega V. And not quite. We scale it by an invariant of our number field, namely we take the absolute value of the discriminant of that number field to the d over 2. Okay? And this now becomes a measure on G A K. And I claim that this measure on GAK is actually well-defined, independent of the choice here of this omega. And why is that true? That's true because this is a top-dimensional form, meaning this vector space here is one-dimensional, so any other choice is just a scaling of this omega by an element in this global field, in this K, right? So if you rescale your omega by this K, then what happens is you get here a product of this vector by which you scale, and you get the v-adic norm of this vector at every place. And there is this product formula that tells you if you take the product over all places of the v-adic norm of any element in this global field, you get 1. Yeah. So the choice did not matter, and this becomes a well-defined measure on the Adele points. And if you have a well-defined measure on GAK and a canonical lattice in there, GK, then of course it becomes a very interesting question to ask, what's the measure, right, of this lattice in GAK? Famous problem for many years, the Tamagawa number problem, which is meanwhile been solved, maybe last cases by Kottwitz or so, I don't recall history, other people know this better than me, but it turns out that the co-volume of GK in the Adele points is always 1. Okay. Okay. So this is kind of nice. We have this measure, which by definition is a product measure over all these local completions. And what we're really interested now is, however, the measure of this fundamental domain F there, right? And the problem is, however, that while this full product here is well defined, I mean, the product over all just finite places here, that's not well defined. This depends on the choice of this omega, and this, of course, then matters for what the volume is going to be. Yeah? So we needed a way to get rid of this dependency and find a way to normalize Haar measure really even at each place. And this is what we did by exploiting that this Lie algebra G has a killing form. Okay, so let me explain this. we define a second measure on the local completion, which we want to call the killing measure. So this is a measure on the group GKV. And yes, Steffen suggested the notation mu dagger for it. Maybe killing reminded him of daggers or so, I don't know. So mu dagger GKV. And how do we define this? Well, basically as before, so we take some differential form coming from such one choice in this one-dimensional space here. We take this completion there, but now we scale by the square root of the absolute value of the determinant of the killing form in this basis that determined omega. So if you write this down, B is our notation for the killing form, EIK, with this form omega determined by some basis just by taking the what's it called, smash product of this basis. And this actually now becomes well defined, because if you scale omega now by, or if you use a different basis here, then this in this new basis you get the old form times 1 over the determinant of the, what's it called in English? The transformation matrix that sends the one basis to the other. Right? So it scales by 1 over this determinant, and the determinant of this killing form matrix here, this scales by the square of the determinant, because it's a quadratic form, yeah, so you sort of have to apply the matrix transpose to the left and the matrix transpose to the right. So by taking the square root, this cancels away, and then you see that the two choices, or the two scalings cancel away. So this really gives you a way to sort of get a unique measure on GKV, which does not depend on choices. Okay. And so now we're trying to reconstruct our Tamagawa measure by using these measures, which are actually already well defined on the local completions. Okay. So we define sort of a total killing measure, mu dagger, as the product of all those local killing measures, mu dagger GKV. Right. And this is again well defined because, okay, so it is well defined because the vectors are well defined, but let me tell you how it relates to the Tamagawa measure. So if we define it like this, then we get just Tamagawa measure times this discriminant of the number field d over 2. Right, so why is that true? Because this is the product over all these guys. But this means we also take the product of all these factors here, and this determinant is again a determinant of a matrix over K. So again, we get a product over all the V valuations, right? I mean, this is the V valuation of an element from K, so this again becomes 1. Yeah? So therefore, it's in fact just the product over all those measures, so it differs from the Tamagawa measure just by this factor of dk to the d half. Okay? Yeah, just again by applying this product formula. Okay, and this is now very nice, because if I now say that my killing measure has a finite and an infinite part, so this is mu dagger infinity for the infinite places times mu dagger finite for the finite places, then I can now, I just need one more line, compute the theorem. So let's do this here. I now take my fundamental domain for the Adele points, f times qg gamma hat, okay? I apply this to my Tamagawa measure, and by this equality, I get from this that the infinity part, the mu dagger infinity of the fundamental group, and now I should put an index gamma into my notation to stress this is the fundamental group 2 for this lattice gamma, because at the moment the other one will rise. This is then the same as absolute value of the discriminant to the d half divided by, and now it's the finite part of my killing measure, applied to this finite part of my fundamental group, fundamental domain, sorry. And now I think you see where this is getting at. So now we need a tiny little bit of number theory. Namely, if my two number fields, K and L, have the same finite Adele rings, that means in particular that they are what's called arithmetically equivalent. So meaning they have the same Dedekind zeta function. And this implies in particular also that they have the same discriminant. And that what? Yeah, so this isomorphism eta only has a chance to exist if GH has the same dimension, of course. So therefore I can write this as DL to the D half. And now how about this guy? Well, that's my isomorphism eta there. Yeah? That sends me G, the AFK points to the AFL points of H. And also, since it's an isomorphism of algebraic groups, it sends the killing form to the killing form. And therefore, I can also replace the denominators of this fraction here and say this is the same as mu killing f of QH of delta. Right? And then I just go back and I will find out that this is mu dagger of the fundamental domain that I chose for delta. Yeah? And since this is just a product measure of killing measures, it really only depends on the local completions there. So this is really the same measure here on both sides of the equation. And this means that gamma and delta have the same cobalt. 1 minute early, but I'm done.
Thank you, Holger. Any questions?
So it seems that basically your proof works in rank 1 in general up to de facto, which kind of subgroups of the center, right?
I think. I mean, I think so. I would have to check, but that we have no center in F4 made anything go away. That was causing trouble. But I believe, yes, that, I mean, if there was another rank 1 symmetric space where the group also has the simply connected group also has trivial center, we would also get it by this method.
Right, but
even
if you have a center, then it can be only up to that.
I think so.
Up to that, the order of the center or the order of a subgroup of the center. That's what it looks
I guess, yes.
kind of interesting.
But yeah, but I'd have to check. But yes, I mean, this would still mean that sort of their volumes are Q multiples of one another, right?
Any answer? Well, let's thank Holger again. Have some coffee.